Okay, welcome. I just want to take a few minutes to go over the pre-labs for the rotating lab. And again, you will all be doing different ones, so make sure you're doing the right one, but I will go over them in order, starting with pre-lab 7. And just to remind you where that is, from the main web page, you go down to labs and pre-labs, and there's a separate link for the rotating lab shown here, and here are all the labs and the pre-labs. So you can find that there. And let me start with pre-lab 7. Yeah, I mentioned this briefly in class, but I wanted to go over a bit of detail so that you do have this. We'll be going over this in a little bit more detail in class, but I have it on the recording, so you have this. And so I asked you to draw the time and domain frequency graphs for a clarinet and the time and frequency domain graphs for a trumpet. So we're going to use this as the characteristic instruments. The trumpet functions as an open pipe, and that gives us the full harmonic series. The clarinet functions as a closed pipe, and that gives us the odd harmonic series. So here's what I basically want you to do for that. I will show you with this. I'll use Mathematica. Let me start with the sawtooth wave, and that's the model we're going to use for the trumpet. Here, UMP. Okay. So I'm doing these backwards in order to what's on the pre-lab. But what I'm doing is I'm going to take a sine of 1x and a half sine of 2x and a third the sine of 3x. And so I've drawn this here, and what I would like you to do is find a piece of graph paper and sketch this out. You see the sine of 1x, that's the black line here, and that has amplitude of 1, and it goes through one cycle, going out to 2 pi here. And you don't have to graph this, you can just sketch this on a piece of graph paper. That's sufficient. And then I'm going to do sine of 2x. And that's going to be twice the frequency. And so that's the green one. And so you see the black curve goes through one cycle. At this point, the green curve goes through one cycle here, a second cycle here. It's got twice the frequency. It's got twice the frequency, but one half the amplitude. Whereas this one goes up to 1 unit, the green curve goes up to a half units, 0.5. And then the last thing I will do is I will do a 1/3 sine of 3, the frequency, and that's the blue curve. And so you see the blue curve goes through one cycle here, 2 cycles here, 3 cycles there. So it's 3 times the frequency, but its amplitude is only a third, which is about 0.33. And so that's what I have. And then on your piece of graph paper, if you add these up, you see that everything's sort of adding positively here. So, I add this amount to the blue curve and this amount to the green curve, this amount to the black curve. I'm going to get a very large number here. And then you see everything comes down to 0 here. So I get a very large number here. It wiggles a bit, comes down to 0. And then again, over here, everything is negative. The blue curve is negative, the green curve is negative, the black curve is negative. That'll give me a very negative number going through 0. And so very approximately, it's going to look something like this. I'll go up quickly and then go down this and then come up. And very roughly, it will look like a sawtooth. And here I'm going to cheat. I'm actually going to use Mathematica to do it. And if I add these up, I've simply added them up, I get the bright red curve here. And I've only got 3 components, but you see that does sort of look like a sawtooth. And if I were to add more, it'd be closer and closer, but you can sort of see what's going on here, that everything is adding up. Whoops, there we go. Everything, let me get rid of that. Everything is adding up positively here. That's why I've got a big amount. Everything comes to 0 here. I've got some positive, negative coming in here, but then it's very negative here. And so I would like you to sketch this. You don't have to plot it. You're welcome to plot it if you want to use a plotting program, but you can just sketch it by hand as you like. And so that's going to be our synthetic trumpet. And the key here is that I use The first frequency I use 100%, the second frequency I use 50%, and the third I use 1/3%. And so this is what we call the time domain graph. This is the amplitude as a function of time. And now I'm going to show you the frequency domain graph because the frequencies are down here. That's this bar chart. And the frequency domain, this is frequency 1 hertz, 2 hertz, 3 hertz. And I have one of the first one, a half of the second one, and a third of the third. So this is what I have. And that will give me my synthetic trumpet. So that's the synthetic trumpet that gives me the sawtooth wave. And now let's try for the synthetic clarinet. For that, we have a square wave, and we're going to do something a little different. For the square wave, I only have the odd ones. So I have 1 hertz, 3 hertz, and 5 hertz. And the 2 and the 4 are missing. And I'm just going to do 3 components. And so let's check and take a look. So the black one, you see that goes through 1 cycle. Okay, and it has an amplitude of 1. Now this one, that's going to go through 3 cycles. That's the green one. So it goes through 1 cycle, 2 cycles, 3 cycles, and the amplitude is 0.33. And then finally, the evens aren't there, so I don't have the 2, I don't have the 4, I have the 5 as the next one, and the blue should go through 5 cycles, 1, 2, 3, 4, 5. Okay, and that amplitude is 0.2, which is 1/5. Okay, and same thing, what I want to do is approximately add these. And so you see here, everything's going to add up positively. So this is going to shoot up quite quickly, but then I've got some positive and negative here. So it'll shoot up quite quickly. It'll wiggle here and then comes down to 0. And then everything goes negative here. It wiggles a bit and comes back up. Okay, and that's my crude drawing of a square wave. And again, you can just sketch this on a piece of graph paper, or if you have something to plot it, that's fine too. Either way, we'll take either one. And so I've done this in Mathematica, and when you add these up, you get the dark red line. And you see everything's adding positively here, so it jumps up very quickly. I've got the green ones going negative, so that pulls it down, it wiggles a bit. Everything comes back through 0 here, and then everything goes opposite negative the other way. And eventually that will look like a square wave, sort of flat on the top. Okay, so that is the time domain graph that gives us the amplitude as a function of time. And now we want the frequency domain graph. And so here I need 3 frequencies because the evens aren't there. And so I've got for the frequency 1, for frequency 1, I've got 1 at frequency 1. Frequency 2 is not there. Frequency 4 is not there. And then frequency 3, I get 1/3, that's 0.33. And frequency 5, I get 0.2. Okay. And so this shows the frequency domain, and this shows the time domain. And so that's what we want. And coming back to the pre-lab, basically, sketch those out, sketch the pieces and then add them up to get the approximately, again, for the trumpet, that's a sawtooth. 1, 2, 3 is good enough. For the clarinet, 1, 3, 5 is good enough. And of course, the primary difference is our one's odd, one's even, and that gives you the very characteristic shapes. Okay, that's what we're looking for there. Okay, enough on the first one. Let's go to the second one. This is the wave tank. And so we want you to list the 4 properties of the waves. That's reflection, refraction, diffraction, interference. And then for each of those, just an experiment that you can measure for light. So light reflection off a mirror, refraction going through from air to water, interference, diffraction, same thing there. And then do the same for sound waves. Give an example for sound waves. I think it should be straightforward, except refraction. The only example I can think of sound refraction is where you have, for example, over a lake, you have the air is warm at one in one case and cold at the other, and that bends the sound. Refraction doesn't, it's not as common for sound waves, but reflection of sound waves, interference of sound waves, and diffraction of sound waves, that all happens. So I think that part is straightforward. Number 9, the resonant flame tube. Here, what I want you to do is to classify which of these are solid, liquid, or gas. And because this is from the book, they give everything all mixed together. There are no patterns. And what we're going to do, we want to look at the gases only, and we want to sort them according to the AMU. That's a simple way of sorting it relative to the mass. And what patterns do you observe? Okay, so let's go through that. And so the gases, let's see. Uh, Steel is a solid, but air is a gas, hydrogen, carbon dioxide, water is a liquid, steel is a solid. We're going to forget about those two, but all the others we will include. And water vapor, that's just a little bit of water and air. So we'll just do air once. We've got 2 airs here in water vapor. We'll just do air once. So we need the AMU for that. Let's start with hydrogen. That's very easy. Hydrogen is just a single proton. Let me see if I can find a periodic table. Yeah, this should do. Okay, so hydrogen, that's just its atomic mass 1 because it's just a single proton. So that's nice and easy. And but in gaseous form, it's a diatomic molecule. It's H2. So hydrogen is 1, but they bond together as 2 hydrogens. So 1 + 1 is 2. So the AMU for that is 2. Okay, the next one, let's do helium. So helium in the periodic table, you see helium is 4. And that is a monatomic molecule, so that's a noble gas, so it does not bind. So the AMU for that is just 4. The next one, let's do air. Air is a mix of nitrogen and oxygen, but it's mainly nitrogen. It's about 85 or 6% nitrogen, a little bit of oxygen. So we're going to just call it nitrogen. Nitrogen is 7 on the periodic table. It's 7 protons, 7 neutrons. So neutrons and protons weigh about the same. So the atomic mass unit, it weighs about 14 units in that. So nitrogen's 14, but nitrogen's a diatomic gas. It's N2. So 14 and 14 is 28. So your air, we're going to take that as approximately 28. We're not going to worry about oxygen. Oxygen, you see oxygen O2, that's 16, that'd be 32, a little bit heavier, but let's not worry about that. Okay, and then carbon dioxide, that's CO2. So carbon is 12, oxygen is 16, and there are 2 oxygens. So 2 oxygens, 16 + 16 is 32, plus 12 is 44, I think, if I got that right. So we're going to put that CO2 at 44. And then once you have the AMU, you can rank them. So classification, I want, solid, liquid, gas, and then you rank them, and you should see a pattern. You should see a pattern as you go from lighter to heavier on this AMU rank. Okay, that's what I'm looking for there. And then I ask you, what is the atomic mass of methane? Because that's what we're going to be using today. It's actually methane mixed with air, so it's not pure methane. But again, it's CH4. So we look in the periodic table, carbon is 12, H is 1, but there are 4 H's, so I got 4 for the hydrogen plus 12 for the carbon, so that's going to be 16. Okay, and then this is obviously a closed tube. So if you're given that pressure wave, And you have to figure out how many wavelengths this is. It's not a quarter. What is the what's the given fine pressure wave? Yeah, we want the wavelength and speed of sound in that case. And is the tube open at both ends or closed at both ends? That's pretty obvious. And then fire will be used in today's lab. So no explosions, please. One of the persons in your group should be assigned to be the fireman. Anytime a flame goes out accidentally, light that immediately so we don't have unburned gas in the lab. And when you're done, you end the project by turning the gas off. You don't blow the flame out, you turn it off because we want to minimize the amount of unburned methane in the lab that minimizes explosions. So do be careful with that, and also be careful as you're reaching over. Don't burn yourself. Okay, next one is the vibrating quad D plates. And if you have a one-dimensional bar, and you can look in your book to see the pictures, but if you have a one-dimensional bar, and assume the center and edges are antinodes. So in that case, it would look something like this. If I draw it, let me make a permanent drawing. So if it's vibrating like this, okay. So then I've got a node here, I've got a node here, and this is an antinode, antinode, antinode. Okay. And so this would be half a wavelength, and this would basically be a full wavelength. And so in that case, even in a one-dimensional bar, you can get an approximate idea of what the wavelength is for that. So, okay, but now that's a one-dimensional case. When we go to a two-dimensional case, it's more complicated. And so for circular disc, look at your book and sketch the first four harmonics. And we're not going to go into detail, but what we found there is that basically the frequency squared, bigger, basically the frequency squared was equal to the number of nodes in the x direction squared plus the number of nodes in the y direction squared. And for a one-dimensional system, it was very easy. There was only the nx direction, and what that meant was the frequency was equal to nx because we could take the square root of both sides. In this case, I can't do that. When I want to calculate the frequency, I can't do that. So I have let's see if I can do this. I'm going to have the square root of these numbers. And so if one of, if, this is, if one of these is 2 squared and the other is 3 squared, I'm going to have an ugly number. And that's why for the one-dimensional case, the frequencies are very nice. If the fundamental is 100, then my harmonics are 100, 200, 300. For two-dimensional objects, that's not the case. I've got these nasty square roots, and that's why I don't have a harmonic series, and that's why things like drum heads and membranes typically do not have a pitch associated with them, because you have all sorts of frequencies are not in any particular pattern, and your brain system does not associate a pitch with them. So that's what we're dealing with here. And let me come back to that. So sketch that, and does the pattern make up a harmonic series? And from your book, you can find what those frequencies are, and they're not in any sensible pattern. So anyway, that's what we're looking for there. Finally, for the fifth one, for the wave interference, what instrument makes a square wave on a time domain graph? And for this one, look back to the first pre-lab that I did. For a square wave, that's how we're going to model a clarinet. And a clarinet functions as a stop pipe, so it only has the odd harmonics, and they will be in the pattern. Its frequencies 1, 3, 5 with amplitudes 1, 1/3, 1/5. In contrast, for a sawtooth wave, that's our synthetic trumpet. That's the full harmonic series 1, 2, 3, 4, 5, and those amplitudes are 1, 1/2, 1/3, 1/4, 1/5, etc. Okay, so this overlaps a little bit with this, and you're going to use the oscilloscope. It also makes some Lissajous figures with some of the laser toys. So those are the pre-labs. And again, let me show you if I go to the class webpage and I go to the class Google Doc. So again, here's the setup, and make sure you're doing the correct pre-lab. So in week 1, these people will start, make this a little bigger. In week one, these people will start on the time frequency plots, and these people will start on the wave tank. And then next week, on the second time around, then you shift down one. And after 5 weeks, everyone will have done all of the labs. So that's the plan. I hope this helps, and we will see you on Monday. Thank you very much, and I'm available on email if you have any questions. So thank you very much.